We're going to continue learning about how to draw Lewis structures. With today's lesson, you're going to learn how to deal with double and triple bonds. So in all the examples that I've showed you so far, when we reached the point that there was 0 electrons left over, when we checked the central atom, it was happy because it was following the octet rule with having 8 valence electrons around it. So now the question is, what happens if you run out of electrons and that central atom still needs more? It has less than 8. To fix that problem, you have to create double or triple bonds. We create double or triple bonds by converting non-bonding pairs from outer elements to create the double or triple bonds. This is where it's so important that you're using a pencil, because you have to be able to sometimes erase stuff in a Lewis structure and reposition stuff in order to make it correct. In a Lewis structure, a double bond is going to be represented by 2 lines. It's 4 electrons being shared back and forth. A triple bond is being represented using 3 lines, and that represents 6 electrons being shared back and forth. All right, what I'm going to do is I'm going to walk you through 3 examples. In the first example, you only need 1 double bond to fix the problem. In the second example, we need 2 double bonds to fix the problem. And in the third example I'm going to give you, it's required to use a triple bond to fix the problem. So now let's kind of go through and solve a Lewis structure for this one. I'm going through and I'm doing my inventory. I'm going to assume at this point you're comfortable with doing the inventories. This one is 24 valence electrons that I need to account for. Nitrogen's the center, 3 oxygens around it. I'm connecting each oxygen with the single bond. Then I'm going to go through and figure out that that was 6 electrons I used up, and now I have a total of 18 left over at this point. It's important to always keep track of your inventory. When I'm adding something into the Lewis structure, I'm subtracting from that inventory because I need to know when I reach that 0 mark. I start to fill those outer shells, and as I'm doing that, I'm subtracting. As I'm adding, I'm subtracting. As I'm adding, I'm subtracting. And now I've reached my 0 mark. When I'm checking nitrogen, it has 2, 4, 6 electrons. It's not happy, and I have no more electrons left to place in the Lewis structure. So now that tells me that I need to start to make double or triple bonds. The tricky part about double and triple bonds is sometimes you can place them in different parts of the Lewis structure. So there's different versions, and all of the versions would still be kind of correct. So you have different options to kind of choose from. Your Lewis structure might look different from the one that I create, but it still might be 100% correct. So I have 3 possible places where the double bond could be created. I could create it using the oxygen on the left. I could create it using the oxygen in the middle, or the oxygen on the right. I'm going to just do it on the oxygen on the left. I'm going to erase any one of the non-bonding pairs from that oxygen using my eraser, and I'm going to create a double bond in that spot. I could have also done the same thing in the middle or on the right-hand side, and I could still produce a correct Lewis structure. When I look at nitrogen now, it has 2, 4, 6, 8 valence electrons. It's now happy, it's now stable. I just need to remember to put my brackets around it and put that charge in that upper corner. Each line is still counting as a bonding pair, so there's 4 of them. There's 8 non-bonding pairs. When I add that up and I multiply that, I get 24, which matches how many valence electrons I needed to have in that diagram. So this problem right here represents something that's called resonance, and that's when there's more than one possible valent Lewis structure for that molecule. When you have resonance, that means there's more than one possible valent Lewis structure. They all have the same number of each type of element present, the same number of valence electrons. The way that they're different is where the double bonds and the single bonds and the non-bonding pairs are being placed. So I have 3 possible versions that I could draw for this. On a mid-unit benchmark or on a test, when you're asked to draw a Lewis structure, any one of those 3, if you drew that, you would get 100% credit for it. But if you're asked for the resonance structures for a molecule, That means you have to draw every single possible version of a Lewis structure for that molecule. So if I was asked for residence for this one, I would make sure to draw all three of them out. I would show all the different places that that double bond could possibly be placed. All right, so in my next example for carbon dioxide, I'm going to be forced to create two double bonds to make the central atom have 8. So I have 16 valence electrons total in CO2, carbon in the center, 2 oxygens placed around it, connect them with single bonds. That uses up 4 electrons, and now I have 12 left over at this point. I start to fill the outer shells. Remember, as I'm doing that, I'm subtracting. As I'm doing that, I'm subtracting, and now I reach 0. When I check carbon, it has 4 valence electrons total. It's not happy because we want to try to bring it up to having 8 to reach that octet rule. So I have 2 different places where a double bond could be placed. Let's say I'm going to just try and I'm going to make this the first double bond in this place right here. So I erased the non-binding pair from that oxygen and I created a double bond. I go back and check. It now has 2, 4, 6 electrons. It's not happy. So it's still not happy with that first double bond that was created. So what I'm going to do now is I see that there's another location to now make another double bond. So before trying anything with a triple bond, if that first double bond doesn't make that central atom happy, and if there's another location to make another double bond, I'm going to create another double bond. So the oxygen on the right, I pick any one of the non-binding pairs from it, I erase it, and I create a double bond in that place. Now when I check carbon, it has 2, 4, 6, 8 valence electrons. It's happy, it's stable. There's 4 bonding pairs, 4 non-bonding pairs. 8 times 2 gives me a total of 16, which is what I initially wanted in the final Lewis structure. In this last example, we're going to be forced to create a triple bond. So in carbon monoxide, you have 10 valence electrons total. Carbon is the central atom, oxygen is the outer one. I connect them with that single bond to use up 2 electrons. Oxygen is my outer one. I fill its shell. I used up 6 electrons, so now I have 2 left over. I place those 2 remaining electrons as a non-bonding pair on that central atom, and now I've reached 0. When I check, carbon now has 4 valence electrons total, so it's not happy. So I'm going to create a double bond by erasing a non-bonding pair from the oxygen, and I created that double bond right there. But now carbon is still not happy. It has 2, 4, 6 valence electrons. So there isn't a second location to make another double bond. So now I'm going to be forced to create a triple bond. I'm going to go back to oxygen. I'm going to erase another non-bonding pair and create a triple bond. Now carbon has an octet. It has 8 valence electrons. So now it's happy. In this Lewis structure, there's 3 bonding pairs and 2 non-bonding pairs. 3 plus 2 gives me 5, times 2 gives me 10. It matches the correct number of valence electrons. So now we need to start to know the properties of single, double, and triple bonds. So a single bond has 2 valence electrons, a double bond has 4, a triple bond has 6. In terms of their lengths, a single bond is the longest, whereas the triple bond is going to be the shortest. In terms of their energies, a single bond has the least amount of energy, whereas a triple bond has the most. In terms of their strengths, a single bond is the weakest, whereas a triple bond is going to be the strongest. All right, so go through and answer these 2 check for understanding questions. So the first one, as the number of bonds between a pair of atoms increases, the strength of the bond between the atoms is going to increase. And as the number of bonds between a pair of atoms increases, the distance between the atoms is going to decrease. The next thing that we need to look at is how to handle drawing Lewis structures for diatomic molecules. So diatomic molecule is a molecule made up of 2 atoms. There's 7 different elements that are diatomic when they're by themselves. So these 7 elements, if you just have a sample of that element, they don't exist as these separate individual atoms. Instead, it's 2 of the same exact element bonded together. The reason why they exist in this diatomic molecular format instead of separate individual atoms is because they're more stable. So for example, if I have fluorine, I don't have individual atoms of fluorine. I have these diatomic molecules of fluorine where there's 2 fluorines bonded together. So a key thing is you have to know which elements exist in these diatomic formats. So first way is you can kind of know their placement on the periodic table. Hydrogen is by itself. The other elements kind of make an L shape in that corner right there. Or you can remember the saying Hankelbrief, hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine are the 7 elements that when they're by themselves, they exist in this diatomic format. So in drawing a Lewis structure for a diatomic element, diatomic molecule, you have 2 of the same exact element bonded together. So I have 2 fluorines, each contribute 7 for 14 valence electrons total. The key thing is you have to kind of treat one of the fluorines as the central one and one as the outer one. So the way that I'm going to visualize this is the purple one is going to be treated as the center and the green one is going to be treated as the outer one. So I connect them with a single bond that uses up 2 electrons. I have 12 left over. The green fluorine is my outer one. I fill its shell and I have 6 electrons left over. I place those 6 remaining electrons on that central fluorine, the one that I did in purple, and now I have 0 electrons left over. When I check that central fluorine, it has 8 valence electrons, it's happy, it's stable, the Lewis structure is done. 1 bonding pair, 6 non-bonding pairs, 1 plus 6 gives me 7, times 2 gives me 14, which is the correct number of electrons that are supposed to be in the Lewis structure. Where this gets a little bit trickier is some of these diatomic molecules are going to have double bonds and some are going to have triple bonds. So for diatomic nitrogen, 2 nitrogens bonded together, 2 times 5 gives me 10. I'm going to treat this purple one as the central one, the green one as the outer one. Just the key thing is you have 2 of the same exact element. Just treat one as the central one as the outer one. Sometimes it's kind of good to make like a note to yourself above the one that you're going to treat as the center and just follow all of your normal steps. Connect them with a single bond. I used up 2 electrons. I now have 8 left over. I go and I fill the outer one's shell completely to now have 2 electrons left over. I'm placing any remaining electrons as non-bonding pairs on the central atom. So I'm going to place those 2 remaining electrons on that purple central nitrogen. And now I have 0 left over. When I check that central nitrogen, the purple one, I have 2, 4 electrons. That's not enough. So that tells me I need to create a double bond. I go to the outer element, the outer nitrogen. I erase any one of its non-bonding pairs, and I create a double bond in its place. Now I go back. That purple central nitrogen is still not happy. It has 2, 4, 6 electrons. There isn't another location to make another double bond. So I go back to that outer nitrogen, I erase a non-bonding pair, and I create a triple bond instead. Now that central nitrogen has 8 valence electrons. It has the octet. It's happy. So now I'm done with this Lewis structure. There's 3 bonding pairs and 2 non-bonding pairs.